this corollary 712, which is the comparison test, and kind of show you how you can go about doing that. I'll give you a couple of examples. So let's go to, I'll do those in the next page. So the comparison test, you're comparing the terms in this series. You're not comparing the series with each other. You're comparing the terms in the series. Okay, so let me give you a couple of examples. So a comparison test. And this is corollary 712. Okay, so the first example that I want to show you is this series right here. And what do you think? What do you think this is going to happen? You think this series is going to converge or diverge? I'll give you a few seconds to kind of think about it. You don't have to answer, but if you think you know the answer, then maybe you can say something. And then another series, which I'll give you right here. This is a 2. Okay, if I told you that one of those series converges and the other one diverges, which would you say converges and which would you say diverges?
Just guessing?
If you had to guess.
I would guess the second one diverges.
This one diverges?
Yeah. No.
Okay, actually it's the other way around. This one diverges. Okay, so let me show you. So if you take, so if you see something like this, just focus on the highest ordered term. Okay, that's pretty much all you need to do. So if you take this, the square root of k over k, that's 1 over k raised to the 1/2, right? Okay, now, so these terms right here are actually okay, I kind of did this wrong. We can do this way. Let me put a 2 right here. Well, let me explain something first. Okay, so I set these up wrong. Okay, I should let me modify these a little bit. Okay, so I'm going to. I don't know what I was thinking. Okay, so what I'm going to do is I'm going to modify the problem a little bit. It's still going to converge either way. Okay, it's still going to converge either way. This is still going to diverge and this is still going to converge. Okay, but if you take the terms, then this is going to be greater than, -4, greater than or equal to 1 over k to the 1/2. Or let me show more steps, okay? Let me show more steps, okay? This is going to equal to k, the square root of k over k, right? because this one has a -4 in the denominator, which makes the denominator smaller. If you're subtracting 4, then this denominator is smaller than that one, which means this number here is larger than that one. Okay, the denominator is smaller means this quotient is larger than that one, greater than or equal to. And this is 1 over k to the 1/2. And what do we know about this series?
Diverges.
Yeah, this one diverges by, how do we know that it diverges?
It's a P series.
Yeah, it's a P series. And P is 1/2, which is less than or equal to 1. Okay, so that means that the first series diverges by comparison test. Okay, now the second series, what should we compare this to? If we just take that right there, what do we get?
1 over k to the 3.
Yeah, and see, that's going to give you, and so what happens is, wait. I can't believe I messed this up again. I don't know what I was thinking. I thought I would put both of them. I'm going to make it a minus again. And then I'm going to tell you something else. Okay. So now this one is smaller than this one now, right? Because there's a minus, it's a -1 in the numerator, so that's going to be smaller than that, which is 1 over k to k third. And 1 over k to the third converges. And that's by, that's again by the P series. P is equal to 3, which is greater than 1. Okay, so that means that 2 converges by comparison test. Okay, also, okay, so what you can also, it doesn't really get to this, but let me just say one thing. It really didn't matter if I had a +4 or a -4 or whatever, or if it's a +1 or a -1 or whatever. The only thing that matters is the highest order term. If it's a polynomial in the numerator and denominator, or adding powers of k in the numerator and powers of k in the dividing by powers of k as a sum or a difference or whatever. It doesn't really matter. The only thing that matters is the highest order term in the numerator and the highest order term in the denominator. Okay, that's the only thing that matters, because there's something called the limit comparison test. Which we're not really going to cover in this class because this is not it's not the topic for this class. But that means you only have to look at the highest order term in the numerator and the highest order term in the denominator, and take the quotient of those two, and then it's going to be 1 over k to some power, and then just look at that power. It's a P series. Okay, just look at that, whatever that power is, 1 over k raised to something power, and whatever that power is determines if it's going to converge or diverge, the whole thing. Okay, but I don't want to get too much into that. So you have that there. but that's limit comparison. If these signs don't do the right thing, like here for comparison, you need this one to be greater than or equal to that to show divergence. You need to show that these terms are greater than or equal to the terms of a divergent series, and then these ones you need to show they're smaller than the terms of a convergent series. Okay, but the comparison is right here with the terms, so maybe I'll make a note of that. So compare terms, not overall series. Okay, so you're comparing the terms, not the overall series. So that means this right here and this right here. Okay. Okay, so let's go on to sequences and series of functions. And the first thing that I want to point out is this definition right here. Okay, so when you're dealing with functions and how they converge, you have pointwise convergence, which means that they're going to converge at each point. But then you also have what's called uniform convergence, which is stronger. Okay, this one is stronger. Okay, so not going to get too much into detail on that, but I just want you to know that uniform convergence is stronger than pointwise convergence. Okay, I think that's the only thing you need to know. The definitions are there in case you're curious. But for what we're doing, I don't think that's really the focus. Okay. Something that I do want you to know is this. It's called the Weierstrass M-test. Right here. So this is really important. And you're going to have to apply this on the exam. So basically, what it's saying is, okay, so here's the gist of it. You have a series involving, so you have so basically you have this series right here, okay, fk of z, okay, and you're looking at that series, right? This is kind of what you're looking at. And you want to know where that converges. So the Weierstrass M-test is a condition for when it converges uniformly and absolutely. And the condition is this, that these terms and the modulus of each of these terms is less than or equal to some constant, some positive or non-negative, either positive or zero constant, each one of these terms in your series, less than or equal to that. And these right here converge. Okay, that's what that means, to converge. Okay, those are your conditions. This dot and that. So each term in absolute value in modulus is less than or equal to some number. These numbers converge. This series involving these numbers converge. If that happens, then the conclusion is that the series involving the functions converges uniformly and absolutely. Okay, I should note right here, this is for all z in some set. okay? It converges uniformly on the set G. So uniform convergence also deals with a set. It has to do with the set. Okay, so that's a really important part of it. So let me give you an example of this. I'm going to go to the homework for that example, okay? No. So let me show you how this works on this set. Okay, so here's the set right here. It's the disk of radius r centered at 0. And here's the functions, okay? So we're comparing that with the Weierstrass-M test, where the Weierstrass-M test has something like this. But here, what we have is the fk of z. Each fk of z is z to the k over z to the k plus 1. In the meanwhile, this set right here is it's equal to the set of z's such that the modulus of z is less than or equal to r. So the modulus of z is less than or equal to r. Now, so this right here is the key to helping you deal with this part here. Because what you want to do is you want to look at this right here and try to get it bounded by something. So you want to examine this and try to see if you can get this bounded by something that actually converges, okay? And the first thing you could do is you could set up like that. Like that. Or let me put that inside because I don't want to do too many steps at once. So I can split absolute values or modulus up into the modulus of the numerator divided by the modulus of the denominator. Okay, the modulus of the numerator, that is going to be less than or equal to, well, let me do one more step. No, I got to do this. Okay, so this is less than or equal to the modulus of z to the kth power, okay? That's the numerator. Denominator, that's going to be 1 minus z to the k. Now, what's the idea here? Okay, so the numerator, this right here, is actually equal to this. Okay, so those two, these are equal. Okay, but this denominator, which is bigger, this or that? This one or this one? Okay, this one, they're automatically working against each other. You have 1 and you have z to the k. They're automatically working against each other. So this is smaller than that. This is smaller than that. But since it's in the denominator, then this whole overall is going to be greater than or equal to that. Okay, now z, modulus of z is less than or equal to r. So that's where we apply this. That's r to the k. This right here, the largest that this is going to be is when let's go from 1. Is when this is 1, so 1 minus r. Okay, this is if k is greater than or equal to 1. Okay, now this goes from 0, but it doesn't matter because because no, I can't go from 0 because then it's oh, wait a minute, it's 2. It doesn't really matter where it starts. You can start it off if you start this from say 5 or whatever over here, then that's still going to converge uniformly. It doesn't. The first few terms don't affect convergence at all. Okay, so now what's going on here? So this is less than or equal to that because modulus is z less than or equal to r. This one right here, if you have k greater than or equal to 1, if I have a 1 here, then this is r to the first power. If it's r squared is going to be smaller than r because r is less than 1, right? It's less than 1. So r squared is going to be smaller. R cubed is going to be smaller than r. R to the fourth is going to be smaller than r. So that means that this part right here, the 1 minus the modulus of z, that's going to be greater than or equal to 1 minus r, because this is when you're subtracting the most. So this is going to be greater than or equal to that. Which means that this is greater than or equal to that. Okay? Which means overall it's greater than, because that's the denominator. Okay. So that's this right here. Now, the other part of the Weierstrass test, so this right here is going to be our MKs. And I'm just going to factor 1 minus r out, so it's just like that. Okay, because this is just a constant. So basically, you think of it this way. This is just a constant. So think of it as some constant times r to the k. Hey, that kind of spells arc. Okay, so think of that as some constant times r to the k. And what can you say about this series? Well, because r is less than 1, this is going to converge. So it's less than 1. Okay, so by Weierstrass test, it converges uniformly. On d bar 0, 1, 0 r. Okay, so that converges uniformly on this set. So basically, we just used the Weierstrass test to show that. Okay, and then you guys get to do these two. Now, if we were to say if 0 to 1, then it actually doesn't converge uniformly on. If you replace this r with a 1, you just say 0, 1, it's not going to converge uniformly on that set. But as long as r is less than 1, then it will converge uniformly.
So, what is MK in this case again?
What's that? Sorry.
MK?
Yeah, MK is this. Right here. Or that.
And then if there's z to the k plus 1, go down to 1 minus z to the k. Is that because, can you explain that again, please? Is that because the minus?
Oh, right here?
Mm-hmm.
Okay, so the modulus of z to the k plus 1, that's going to be greater than or equal to 1 minus the modulus of z to the k. Okay, that's a version of the triangle inequality. Hold on. You might have seen this before. Z1 plus Z2 is greater than or equal to the modulus of Z1 minus the modulus of Z2. That's a version of the triangle inequality, because here they're working together. Here they're automatically working against each other. Well, actually, we don't know if they're working together or not, but they might be partially working together. But here, automatically, they're working completely against each other. So the same thing with this one. But this one is greater than the modulus of this, because the modulus of that is less than or equal to R. Okay.
Okay, got it.
So that's why this is greater than or equal to. So that means we go less than or equal to, because this is in the denominator.
Okay. Thank you.
And I'm just going from 1, because I can go here. It goes from 0, so that's a little technicality. But convergence of a series does not depend on the first million terms or whatever. It depends on what the end of the series, which is going off to infinity. It just depends on that. So it doesn't depend at all on the very first term. As long as the first terms are defined. If they're not defined, then it just becomes kind of awkward, because that was not a very well stated problem. So that's the Weierstrass-Hem test. And the next thing I want to look at is power series, because that's what this section is about, is power series. So power series look like this. They're of that form right here. And this is a very important example right here. And it converges absolutely for modulus of z less than 1. Because that's just a geometric series. And you can use the Weierstrass-Hem test to show that it converges absolutely and uniformly for modulus of z less than or equal to R. Okay, you can use the Weierstrass-Hem test to show uniformly for modulus of z less than or equal to R. Converges absolutely there. It doesn't converge uniformly on modulus of z less than 1. But if you take a number smaller than 1, between 0 and 1, then it's going to converge uniformly on that. Okay, and the argument is similar to what we just did. Now, the interesting thing is that where it converges looks like is typically going to be a disk. So here, let me draw a picture. So let's say this is Z0 right here. So what's typically going to happen is there's going to be a disk. And what will happen is theorem 731, which you've already heard of something called the radius of convergence. Which is capital R. And that's actually going to be the radius of this circle. And what we're saying right here is it converges absolutely and uniformly inside that circle. Absolutely and uniformly for modulus of z minus z naught less than equal to R, for if any R that's less than capital R. And the other thing, which is on the next page, is that we'll diverge out here. for modulus of z minus z naught greater than r. It's going to diverge out here. Diverges. So inside, it's going to converge. Outside, it's going to diverge. The boundary is all this now. So contrast that with what you learned from calculus, where calculus you have some number line, and it's like an A or something, and you're looking at a series like this. And then you have like this radius of convergence where it's going to converge anywhere inside, diverge outside. And then you're supposed to check the endpoints, right, to see if it converges at each of the endpoints to get like an interval of convergence. So this is the real numbers thing. This was still called the radius of convergence, even, and maybe you're like, whoa, is it a circle? Oh well. Here it's a circle though, with complex numbers. And instead of just being endpoints that are up in the air, you have the whole circle up in the air. The disk inside, it's going to converge in there, and outside it's going to diverge. But here you have the whole boundary of the circle that you don't know what it can do. Now, in some cases, you know. In other cases, it's not as clear. But it could go either way. So there's the other part. It diverges from outside. This means it diverges outside. And here it's telling you that that number is called the radius of convergence at R. There are ways of finding the radius of convergence. Let's talk a little bit about that. This is the only one I could find that they give you in the book for finding the radius of convergence. This is the root test. But the ratio test also works. So let me try to explain how this works. I'll go to the previous page here, and I get a couple of examples for this one. And so let's say find the radius of convergence. Okay, and then the first one would be this right here, z to the k over 7 to the k. Okay, so now what you can do is there's a couple of ways that you can proceed. One of them is the ratio test, and the other one's the root test. Okay, with the ratio test, you're taking the limit as n goes to infinity of a n plus 1 over a n. Well, it's going to be modulus of those two. So if you put k plus 1s in here, you're going to get modulus of z to the k plus 1 over 7 to the k plus 1. That's going to be modulus. And then the denominator for a sub n, whoa, dang it, I put k's instead of n's. Sorry about that. Okay, let me put n's now. N plus 1, and this is n plus 1 there. And in the denominator, you're going to get z to the n over 7 to the n. And what's going to happen is z to the n plus 1 over z to the n, that's z. And 7 to the n plus 1 over 7 to the n, that's 7. So you're going to get this. Okay, now that's going to be your L. And remember, if L is, you're going to converge if L is less than 1, or modulus of z less than 7. And you're going to diverge if it's greater than 1, or modulus of z greater than 7. So that means the radius of convergence is 7 in this case. Another way you can calculate this with the ratio test is taking it directly, is flip this over and only take the coefficients. Okay, so what I mean by that is the coefficient, when you put an n in here, ignore the z part, and you only have 1 over 7 to the n, right? And here you have 1 over 7 to the n plus 1. So that ends up being 7 as the radius. So you can flip it, take the reciprocal, but only look at the coefficients, since that's going to give you the radius of convergence. Okay, so with root test, with the root test, that's another route you can go. And you can apply this formula here. So let's look at this. 1 over the limit of the kth root of the coefficient. This is coefficient. Okay. So this root test here, you're just looking at the coefficients. You're getting at the CKs. What the? So limit as k goes to infinity of 1 over the kth root of the modulus of ck. Which right here, ck is, what's ck? What's the coefficient of this? What's your ck? Anybody? Okay, so it's the ck is going to be the part that's ignoring the z part, right? So that's basically a 1 there. So it's 1 over 7 to the k. This is 1 over 7 to the k. Now, what's the kth root of 1 over 7 to the k? Okay, so that ends up being 7. So again, you get the radius is 7 either way. This is the root test, and this is the ratio test. Let's do a couple more examples. Let's do this one right here. And here we have z to the k over k factorial. What do you think the radius of convergence is going to be for this one? Can you guys hear me, by the way?
Yeah, we can hear you.
Okay. Does anybody want to guess what the radius of convergence will be? Do you recognize this series? This is exponential of z. Okay, this is exp of z. Is this exactly? And the radius of convergence is infinity. If you take the, if you apply the ratio test, then what happens is the numerator is z to the k plus 1 over k plus 1 factorial, and the denominator is z to the k over k factorial. And that is the numerator is gonna basically, everything cancels out except a z in the numerator and a k plus 1 in the denominator. And so that's gonna be 0. And since 0 is less than 1, that means the radius of convergence is infinity because it converges everywhere. Everywhere in the complex plane. Okay, so that's the first, and this is a function that you need to know how to do. Okay, this next one will be this right here. K squared is z to the k. And if you take the limit as k goes to infinity of this one, you're going to get, you put k plus 1s in here, that's going to be k plus 1 squared z to the k plus 1. And that's going to be over k squared z to the k. Okay, this part right here, as k goes to infinity, this is going to go to 1. So in the end, you're going to end up with just that. Okay, and then, so that's your L. If you set it, if you force it to be less than 1, that's where it converges. And if it's the greater than 1, it diverges. So that means the radius of convergence is 1 for that function. Okay, so let's talk a little bit about power series in general. And here's some power series, the power series that you already know. I told you the exp of z, that's this one right here. Okay, there's a power series that you should, that's similar to what you've learned in calculus, except the x to the k has been replaced with a z to the k. I want to put a note here at the bottom. You're allowed to give the first, as an answer, the first 4 non-zero terms. Okay, so you don't have to write it out like this. So you could write it out like 1 plus z squared over 2 plus z cubed over 3 factorial. Okay, now if you do that, that's even better. And if you do that, that's even better. Okay, but you don't need to do that. So if you, and then plus dot, dot, dot. Okay. and then some plus dot dot dot. And then I'll accept, so if this is the answer, I'll accept this right here as the answer. Okay, so that's what that means. Another one would be sine z. And for that one, I'm not going to even worry about the formula. You can look that up if you want. But that's z minus z cubed over 3 factorial. So now we've skipped a couple of terms, the 0 term and the 1 term, but those are not non-zero terms. So I want 4 non-zero terms. So I do 2 more terms. So z to the 5th over 5 factorial. And what do you think the next term is?
Z to the 7 divided by 7 factorial.
Exactly. So z to the 7th minus over 7 factorial, and then put dot dot dot. Okay, so 4 non-zero terms plus a dot dot dot. Cosine z. You guys remember what that one is? So that's 1. It starts out with a 1 instead of a z. And then minus z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial plus dot dot dot. Okay, one thing that you can do is you can use these. Oh yeah, and a really important one, probably the most important one for this class is the 1 over 1 minus z, because that's the geometric series. Okay, so this one is k equals 0 to infinity of z to the k, or 1 plus z squared plus z cubed, and so on. Okay, one thing that I want to point out here regarding power series is you can get new power series from old ones. And I want to give you a few examples. So let's suppose we want the power series for z times cosine z. Okay, so what you can do is, okay, that's z, and you can write down the first few terms of the cosine z. What are the first few terms of the cosine z power series?
1.
Yes.
Z squared over 2 factorial. Z to the 4th.
Yes.
4 factorial.
And then is that right? And then so what you could do is you have this z right here. You can just distribute that z in. So it's z minus z cubed over 2 factorial, and then distribute the z into here. You get z to the 5th over 4 factorial, and then distribute it into there. You get z to the 7th over 6 factorial, and then just put dot dot dot. Okay, so that would be a way of finding z times cosine z. Another thing, here's another method that you can use. Let's suppose that you want exp, you want to get the power series for this squared. Okay, so what you can do is you can write down its power series. If you have 2 functions, or if you have this squared, you can write down the power series for each one. like this way, right? Write down like that, and then just multiply these together. So the only way that you can get these two is that, right? So that's only way you can get a constant term. Now there's two ways to get a z term. There's this times this, and then there's this times this times this. So that's going to be 2z. And then let's see, there's too many ways. There's a lot of ways to get z squared. There's that and that for z squared. And then there's this times this, and then there's that times that. So that's going to be, it looks like that adds up to 2z squared. Okay, and then you just have to get one more to get the 4. But with a problem like this, I might say, oh, 3 is enough. But just get one more. I'm not going to get too much into that because I think you understand what to do. So it would be, so what you'd have to do is this one here times that one. And then this times, so that's would be the first one. And then the second one would be this and this. And then the third one would be this and this. And the fourth one would be that and that. And then multiply those all together and add those together to get the next term in the series. And then that's 4, and then you've got enough. Okay. And so there's if you have like a monomial like this, then you can easily distribute that in. If you've got 2 power series that you know, then you can just put them like this and just multiply the terms. Get 4 and you're good. Another thing is you can take derivatives and integrals. So for example, I know that 1 over 1 minus z is equal to this power series, right? Or z to the k. Well, let me do a couple of things. So if I can change this to a plus c, but what that's going to happen there is, hold on. Is that's the same as 1 minus a negative z, right? So if I have 1 over 1 plus z, that's the same as 1 minus a negative z, which means that here, if I replace this z with a negative z, then it's going to be the same. And then I could write it like that. Okay, so that's just changing it a little bit. Now I can take the integral of this. What's the integral of 1 over 1 plus z? That's the natural log of 1 plus z, right? But I integrate these terms here. And I get that. So if I integrate that, I get z to the k plus 1 over k plus 1. And that goes from 0 to infinity. So, okay, and so then you get something like that. You can also turn this around and approach the problem this way. Okay, what is the function represented by, let's say that we have k, z to the k plus 1. Okay, so a function like that. So, wait a minute. Yeah, okay, so if I had something like this, okay, then would you recognize that as the derivative of something?
Z to the k.
Z to the k.
That's the derivative of z to the k, right? It's right here. So I can factor z squared out. And I get that, right? And then I can integrate that. And I just get z to the k. But then what's this series right here?
Geometric.
Yes, that's geometric. So I just get that. Yay.